So what we've seen so far is that parametric equations are two functions, one function that describes the behavior of the x values and another function that describes the behavior of the y values. And those functions both depend on a third variable, t, which we call the parameter. Okay, the x function and the y function can be completely separate functions independent of each other. And that's generally the idea of the parametric equation, is we want these two independent functions, and they both share a common variable t. But sometimes it is possible to take these two separate functions and combine them so that they are just functions, just equations in terms of x and y. So that means we're able to remove t from the equation. So instead of having two equations depending on t, we can rewrite the two equations as one, where you have either y depends on x or x depends on y. Okay, not always going to be the case, but sometimes, often we'll be able to do this. And how we do that, there's several ways that we can do that. But we usually refer to the process or what we're trying to do as eliminating the parameter. So we want to remove it and combine the equations together. So let's look at a few examples of how we can eliminate the parameter from a set of parametric equations. For our first example, we have x is equal to 3t plus 2, and y is equal to negative 6, natural log of t, plus 5. So this first equation, x equals 3t plus 2, that's just a linear equation. Okay, x is a linear function of t. And our second y equation is y is equal to a negative 6 natural log of t, and then plus 5. So we have a linear equation, a linear function, and then we have a logarithmic function. So one way that we can combine these together is we can pick one of the equations, it doesn't matter which one, solve it for t, and then substitute what we get for t into the other equation. Okay, so when we think about which equation we want to solve, we usually like to go with the equation that would be the easiest to solve algebraically. We'd like to avoid getting things like taking square roots of both sides, because if you take the square root of both sides of an equation, you get a plus or minus. So that has some problems. That brings into the problem. So if we look at x equals 3t plus 2 and y equals negative 6 natural log of t plus 5, which of those equations would be easier to solve for t? Technically, we could do both, but it would probably be easier to solve the linear equation. So let's do that. So we're going to take x equals 3t plus 2 and solve it for t. So that means we're going to subtract a 2 from both sides, and that gives me x minus 2 is equal to 3t. And then we're going to divide both sides by 3 to isolate the t. So that results in t equaling x minus 2, that whole expression divided by 3. So I'm going to take that fraction, x minus 2, all divided by 3, and I'm going to replace it. I'm going to plug it into the y function for the t value. So if y is equal to a negative 6 natural log of t plus 5, then that means my combined equation, where I've eliminated the parameter, is going to be y equals a negative 6 natural log, but instead of t now, I'm going to replace that t with that fraction. So I'm going to have negative 6 natural log of x minus 2, x minus 2 over 3, and then all of that plus 5. So y equals a negative 6 natural log of x minus 2 over 3 plus 5. And so this gives me a single equation without the extra parameter that describes y as a function of x. And again, we could have done it the other way. We could have solved the y equation for t. It just would have involved dealing with exponents. Okay, which again is still possible algebraically. It's not too bad, but it was easier to solve the x equation. All right, let's look at a second example. So we have x is equal to a negative 2t squared plus 3t minus 4, and y is equal to t plus 7. So the x equation is a quadratic function because we have a t squared, and the y equation is just a linear function because we just have a t. All right, so which of those is easier to solve for t? Technically, we can do both. If we solve the quadratic equation, we are going to end up with a plus or minus, and we kind of want to avoid that. So this time, let's solve the y equation for t. And this one will be pretty easy. To isolate the t, we just need to subtract both sides by 7. So we're going to end up with y minus 7 is equal to t. And I'm going to take that y minus 7 and plug it into the t's in my x equation. So I'm going to have x is equal to a negative 2 times y minus 7 quantity squared plus 3 times y minus 7 and then minus 4. I could simplify that, but it's not necessary. I'm just going to leave it like that. So that now describes x as a function of y, as a quadratic function of y. So it's no longer expressed as a parametric equation. It's just one function, and there's no parameter. All right, so again, we've looked at two examples. One example where we solved the x equation for t. The other example, we solved the y equation for t. Okay, so again, you can do it either way. Let's look at one more example. This one's going to be a little different. So this time we have x is equal to 9 cosine of t, and we have y is equal to 4 sine of t minus 1. So solving, if we try to follow the same process, that means I'd have to solve either an x equals 9 cosine of t for the t, or I'd have to solve the y equation for t. But in both of these examples, the t is inside a trig function. It's inside the cosine or it's inside the sine. Right? It's the cosine of the t. It's the sine of the t. And in order to do that, in order to isolate the t, in either of those, it would require using an inverse trig function. Okay, so for example, if we tried to do the x equation, since it has a fewer terms, so x equals 9 cosine of t, we divide the 9 over, so x over 9 is equal to the cosine of t, and then I take the inverse cosine of both sides, so I have t is equal to the inverse cosine of x over 9. And then I could take that and plug it into the y equation, but I really don't want to do it that way. Okay, I don't want to have to incorporate inverse trig functions if I don't have to, because remember, our inverse trig functions have restricted domains and ranges. Okay, remember that inverse cosine is only defined between -1 and 1, and it only produces values between 0 and pi. And similarly, we have domain restrictions and range restrictions for inverse sine. So I want to avoid taking a function without any restrictions and rewriting it as something that requires one, or requires restrictions. Okay, so do I have, in order to do something different, do we have some sort of relationship that connects sine and cosine? And it has to be a relationship that is always true. Okay, well, just that idea there, a relationship that is always true, that sounds like an identity. That phrase, an equation that's always true. That's what an identity is. So what identity do I have that connects cosine with sine? Well, if we look at our Pythagorean identity, that's right, our Pythagorean identity says that cosine squared of theta plus sine squared theta is equal to 1. Okay, that's our Pythagorean identity. Now, I don't have cosine squared and sine squared in this problem, but I do have cosine and sine. And so I could kind of take both of my equations, take one and solve it for cosine, and take the other and solve it for sine, and plug it into the equation. Okay. Now, my parametric equations are involving t, right? So cosine of t, sine of t. And usually we write the Pythagorean theorem in terms of theta, but it doesn't really matter. Theta is just a variable. We could use whatever letters we want. So instead of cosine squared theta plus sine squared theta, you could just think of it as cosine squared t plus sine squared t. Okay, so let's take our two equations, solve them for cosine, solve them for sine, and then plug them into our problem. So if we have x equals 9 cosine of t, that means cosine of t is equal to x over 9. And if we do the same thing for the sine, for the y equation, y equals 4 sine of t minus 1. So if we add the 1 to both sides, we'll have y plus 1 is equal to 4 sine of t. To isolate the sine, we divide everything by 4. So y plus 1 divided by 4 is equal to the sine of t. So I now have an expression for sine and an expression for cosine. Let's plug those into our Pythagorean identity. So Pythagorean identity says we have cosine squared. Well, cosine is x over 9. So that means I'm going to have x over 9, that fraction squared, plus sine squared. Well, sine is the same thing as y plus 1 over 4. So I'm going to have that fraction, y plus 1 over 4, the whole fraction, squared. And I know that because of the identity, the sum of all of that has to equal 1. And I can leave it there. I will simplify this a little bit. For each fraction that you square, you can square the numerator and the denominator. So that means I'm going to, instead of x over 9 quantity squared, I could rewrite that as x squared over 81, because 81 is 9 squared, plus, now I have y plus 1 squared. I can't really simplify that any further without foiling it out. I don't want to do that. So I'm just going to leave that as y plus 1 quantity squared divided by 16. I get the 16 because that's the 4 squared, and that's equal to 1. So x equals 9 cosine of t, y equals 4 sine of t minus 1 could be rewritten as x squared over 81 plus y plus 1 quantity squared over 16 is equal to 1.